Welcome to AP Video Unit 1.7, video number 1. We're looking at atomic and ionic radii. And so that's our periodic trends for atomic and ionic radii in particular. And so our essential prompt is to use Coulomb's law to explain the periodic trends for atomic and ionic radii. So in order to get there, in order to answer our essential question or essential prompt in the summary, we're going to look at some main ideas, questions, and prompts that you should implement in your summary statement. So the first part, it says to list factors that affect periodic trends. So when we're looking at periodic trends, we see we have several different types of trends. We have ionization energy, electronegativity, atomic size, ionic size, electron affinity. We have several trends that we will look for, and so what we see on a periodic table is as we move across the periodic table, we can see trends for certain things, and as we move down a group on a periodic table, we can see trends for certain things, and so those trends are affected by some other factors that and so we just have to be able to explain those. So the explanation of trends. So for period trends, and when I say period trends, I mean we're moving left to right across a period. Now, I guess you could move either direction, right to left or left to right, but I'm going to be referring to left to right. So this is period 1, period 2, period 3, period 4, so on and so forth. And we see that right here, period numbers are listed. And so that's not a very hard concept to gain. So what affects trends for, what affects period trends? All right, what's going to cause factors to change that we see a certain trend across a period? And there's only one, and that is nuclear charge. The nuclear charge of atoms on the periodic table increases from left to right. And we talked about how to calculate the effective nuclear charge in a previous video. I have that formula here, and we saw that the effective nuclear charge for group number 1, it had an effective nuclear charge, let's say ZFF, of 1, 2, and then we moved over here to these. They were 3, 4, 5, 6, 7, 8. And so what we see is the effective nuclear charge increases as we move left to right across the period. And because that effective nuclear charge increases, we're going to be able to explain why other periodic trends occur. Okay, so one of the things that we are looking at when we are considering nuclear charge is we're looking at the attraction valence electrons have for the nucleus, and in order to determine the attraction, we look at binding energy from the photoelectron spectrum of a particular atom. And so here I just want to compare oxygen and fluorine. Now we will notice, if I remove all of my markings here, you will notice that oxygen and fluorine are in the same period. Here they are right here. So they're side by side. And we know that oxygen has an effective nuclear charge of 6, and fluorine has an effective nuclear charge of 7. So as we move across a period, things that I want you to notice about oxygen and fluorine is that fluorine does have more protons. That's what's given it its higher effective nuclear charge, but it has the same number of core electrons. Also, it has the same number of energy levels. So we can clearly see that we have energy level 1, energy level 2, energy level 1, energy level 2. They both have the same number of energy levels. So the distance the valence electrons are from the nucleus is roughly the same. And when we talk about atomic radii, we're going to see that that there is a slight difference, but we're going to be able to explain it from this PES that we have here, the photoelectron spectrum that we're about to show. So, so let's go ahead and take a look at that. So if we're drawing the photoelectron spectra for oxygen, and I want to make sure I show that electron configuration there. We're going to show our 1s peak, and we'll show it to be this high. Well, let's do something. I want to move that over a little bit. Let's move it here. So this is our 1s peak. How many electrons is that representing? If you know that's the 1s peak, you should know that's 2 electrons. And then we're going to show our 2s peak, and it's going to have less binding energy. Why? Because the second energy level is further away from the nucleus, and so it's further away from those electrons are further away from the attraction of the nucleus. And then what we're going to have is 2p4. All right, and 2p4 may be right here. Let's say it's right here. All right, and notice that the peak height got a little bit different, a little bit higher. Why? Because there's more electrons. And so we see in for the second energy level, we have 2 electrons and 4 electrons, or 6 electrons. Okay, so what happens if we are comparing fluorine with the same thing? Well, fluorine has more protons, all right? So it has a higher nuclear charge. The energy those 1s electrons have, the binding energy those electrons have for the nucleus is greater. So they're moved over further to the left. Remember, binding energy is higher over here. So this is, we will say this is like 1,000. We'll say this is 0. We're just throwing some numbers out there. And so then if we looked at the 2s peak, it would be higher than the 2s peak for oxygen. And then if we looked at the 2p peak, it would also be higher energy than oxygen. All right, slightly larger, because why? It has 1 more electron. So we have to understand that the binding energy for oxygen is higher. Why? So we're going to say here, binding energy, this is annotating this, binding energy for fluorine, rather, is higher because of higher nuclear charge. All right, and so another bullet point that you can make on here, more attraction. All right, these electrons have more attraction for nucleus. So when we're considering trends for atomic size, as we will here, we're going to see how this increase in attraction affects the differences in the size between fluorine and oxygen. But from a conceptual standpoint, and as we deal with every trend, we're going to have to understand this phenomenon here. So if we looked at it from the oxygen standpoint, and we're just going to be looking at these valence electrons, we see, and these are both valence electrons right here. Maybe I'll undo that. That doesn't look very good. So yeah, right here, this peak and this peak, these are our valence electrons. And so what we see is the binding energy for oxygen is less because the nuclear charge is lower. All right. And what does that mean? It means lower attraction. So those electrons have a much smaller attraction, or they have a smaller attraction. The valence electrons for oxygen have a smaller attraction to the nucleus than do the valence electrons for fluorine. Fluorine has a higher attraction. So that's very important to understand that trend. That's what we're talking about with nuclear charge. This means the attraction or binding energy valence electrons have for the nucleus increases left to right. We can see that nuclear charge increased left to right. We saw oxygen has a smaller nuclear charge. Fluorine has a higher effective nuclear charge, and therefore it has higher binding energy and also more attraction. The valence electrons have more attraction to the nucleus. And as a matter of fact, all their electrons have more attraction to the nucleus with their respective peaks. All right. And what I mean by that is the 1s peak for fluorine has higher binding energy than the 1s peak for oxygen. Okay, so let's look at another, and we're going to look at the group trends and what affects group trends. So there are two things that will affect group trends. And so one is the addition of energy levels. The valence electrons for atoms moving down a group are in higher energy levels, a further distance from the attraction of the nucleus. And so this is going into Coulomb's law once again. Here we saw the charged particles and for nuclear charge, we saw a higher nuclear charge. We have more protons, more electrons. It increased the force of attraction. Here we're looking at for group trends. We're looking at this component right here. We're looking at radius. All right, we're looking at radius because as we move down the group, we're increasing the number of energy levels, and so those valence electrons are further from the nucleus. And if they're further from the nucleus, the force of attraction will decrease. All right. So nuclear charge, we have more protons and neutrons. We're affecting the numerator here. That increases the force of attraction. For adding energy levels, we're increasing the radius, which decreases the force of attraction. So very important to note and understand what's causing those things to happen. So the addition of energy levels, moving down are on higher energy levels, a further distance from the nucleus. So what does that look like? So here we have the photoelectron spectrum for that. So notice we have lithium and sodium. They're both in group 1. And just to highlight this, even though you can go to your periodic table, we see lithium, and then below lithium is sodium. So lithium, its valence electrons are in energy level 2, whereas sodium, its valence electrons are in energy level 3. So we can see that very, very easily. Also, to highlight that, I have a Bohr model here to show that we have energy level 1 and energy level 2, and then here we have, and just to color code this, 1, 2, 3. So we can see that very, very easily. So let's take a look at what the binding energy looks like. Now we noticed that on the period trend that fluorine had a higher nuclear charge, and its binding energy for every suborbital, 1s, 2s, 2p was higher binding energy. When we're looking at lithium and sodium, well, lithium does have more protons and neutrons, and so the attraction of those core electrons are going to be higher than the attraction of the core electrons in lithium. But let's take a look at this real quick. So we're going to draw lithium, and we'll show the 2 electrons in the 1s, and then we'll show the one electron in the 2s, and we'll show this over here somewhere. There we go. So now, if we were going to draw and we are going to draw the photoelectron spectra for sodium, and I hope you notice I'm color coding these by the outline of the picture. So this is why I'm drawing lithium in blue and sodium is going to be in pink. So you can see that the same thing happened here. I didn't highlight that, but so what you can see is that sodium does have more protons, and it would also have more electrons if this were a neutral atom, and it is. We see all the 11 electrons. We see that the 1s peak is going to have a little more binding energy because there's more protons there. So this 1s peak for sodium is actually going to be a little bit to the left or in higher energy. We're just going to make up some fictitious values here. 1,000 megajoules per mole. And then, so what we'll see is even the same thing for the 2s. So the 2s is going to have how many electrons? 2, 4, 6, 8. But we see that 2 of them are in the s peak, and then we would see 6 of them in the p. Now, so far, all of these electrons are higher in energy than the valence electron for lithium. But wait, now we're going to talk about this extra energy level. So notice this is 1s, this is 2s, this is 2p. This is 1s, this is 2s. What do we know about sodium? That's right. It has an additional energy level. That energy level is further from the nucleus. What is that going to do to binding energy? Well, that's going to cause the binding energy of that 3s electron to be further to the right or have less energy than the 2s of the lithium atom. And so we're going to see that this is going to still have one valence electron because it's in energy level 1, but this would be the 3s electron, but for sodium. Notice it's in a higher energy level. It's further away from the nucleus. Its binding energy is less, and therefore, it has this electron has less attraction. Let me write this down. This electron less attraction than, let me see if I can do that a little better, than this guy. All right. So it has less attraction for the nucleus. Those valence electrons there, or that one valence electron, has less attraction for the nucleus than the 2s electron for lithium. And why is that? Because it's further away from the nucleus. How do we know that? We explain that with Coulomb's law. Coulomb's law tells us that as we increase the radius, the force of attraction does what? Decreases. And we related that to binding energy on the photoelectron spectrum for both lithium and sodium. So hopefully that helps you understand and guide you as we start talking about these other periodic trends, because you're going to have to use this idea to explain the other trends that we have for atomic radius, for ionization energy, for electronegativity, electron affinity, all of those. Okay, the other thing that affects group trends is the shielding effect. Okay, in the shielding effect is the decrease in attraction between an electron and the nucleus in any atom. And so what we see here is if we are adding, and these two things go together, if we're adding energy levels, what happens is we have more electrons in the path. We're adding more electrons that are blocking or shielding the attraction of the nucleus for the valence electrons. So here is an illustration. We see that we have our valence electrons here, and while they are attracted to the nucleus, they are being repelled by core electrons. All right, and these core electrons are actually reducing the attraction these valence electrons would have if they were not there. And as we add more energy levels, so if we add another energy level here, and obviously this is not going to be correct, and we had more electrons, let's put a different color, maybe this pink one, and we would see there's the same attraction for this, but then there's the same repulsion from this one. So as you add more and more core electrons via adding additional energy levels, you're going to see an increase in the shielding effect. So the attraction that the electrons have for the nucleus becomes less and less because the repulsion of the core electrons that take place. And so that is something that you have to remember. I'm not going to relate that to the photoelectron spectra just because it doesn't show it. It will show up on there, but it's not as easy to explain from that perspective as it is adding additional energy levels. Just know that when you add additional energy levels, you're adding more core electrons, and that because you're adding more core electrons, those electrons are repelling the valence. Those core electrons are repelling the valence electrons and decreasing the attraction those valence electrons have for the nucleus. Very important points. So anytime you're asked to select what would cause a period trend, the only answer that you would show for a period trend would be nuclear charge. If you have a multiple choice question on a period trend and you see those two atoms are in the same period, why is it? You're looking for the word nuclear charge. If you're looking at group trends, there's only two things that can explain this. One is the addition of energy levels, and sometimes they explain this through atomic size as well. But and we'll talk about that because that's what this video is about. And then the shielding effect. All right. So those two things are your explanations for group trends. If you know that, then you can go a long ways towards reaching mastery on your test. So the next thing, and so let's just make sure before we go on that we looked at everything. So we list factors that affect period trends. That was nuclear charge. We're going to show the annotated PES for period trends. When I say annotated, that means you're drawing a sketch of the photoelectron spectra. You're making a note on there so that you can see different things. Here, I annotated that the binding energy is greater than or less than, and I talked about attraction. You should also have a picture of that in your notes. And then list factors that affect group trends. I want you to define the shielding effect. That's easy to do. It's already in there, so just put that in your notes. Show annotated Bohr model that describes the shielding effect. So when I say the annotated Bohr model, I want you to show this picture here, but I want you to write information in there that lets me know that you know that there is attraction. The attraction the valence electrons have for the nucleus is reduced due to the repulsion of the core or inner electrons. All right, and so make sure you add those things, and then use Coulomb's law to explain group trends. Yeah, you can use Coulomb's law to explain both group and period trends. To explain group trends, though, you're going to note that you're adding an energy level, which increases the distance those valence electrons are from the nucleus, which does what to the force of attraction? Decreases it. And if it decreases the force of attraction, what is that doing to the binding energy? It's decreasing the binding energy. So there's less attraction. All right. So it's very important that you understand those relationships. If you were going to explain period trends in terms of Coulomb's law, then you would want to do that by showing that the charged particles, all right, we're increasing the number of protons and electrons across a period without increasing the distance. So what is that going to do to the force of attraction? That's going to increase the force of attraction. All right, we don't have to know exactly what that force is, but we definitely need to know that it does increase or decrease based on certain criteria. And so we've covered all of that. That's all I'm going to cover in this video. I feel like I covered enough. And then we will move, even though I didn't get to atomic and ionic radii, this will be video 1 for that. And the next one, we're going to talk about atomic and ionic radii and just knowing how we are coming up with our trends. We should be able to explain period trends and group trends. Thank you for watching. Please like and subscribe.